Yeah, today we're going to discuss several real-world projects that we and our company and actually I have developed and challenges faced. Let's start with LLM-powered data extraction. Nowadays, we have a lot of data, and a lot of customers have their platforms and so on. They can have users, products, and so on. And an example of this data is a review, whether it's a product review or someone else review. And in this part we're gonna use LLMs to actually extract relevant metadata to understand this text unstructured data. And actually to show the insights, we're gonna take a small open source data set, Amazon customer feedback, and with over 35 million records, and we're gonna use a subset of it for our journey. Yeah, we mentioned that we're gonna extract a meaningful data, but in order to do so, we have to define the data model. On the right, you can see a pretty standard way of defining the model in Python is identity model. And on the left, we can see a more human level description of what each field means that is actually used further to create prompts. Now let's start with the regression. Well, and actually here what we have stars of review of the product, and we have several supporting features. And let's start with the regression task. That is actually source prediction in our use case. We predicted stars based on the previous data structure and utilized RMSE as our main measure. And RMSE computed on predictions of the LLM using the zero-shot technique without prior model fine-tuning resulted in 0.76. One may say that it's not that close to 1, but actually for our test, having that is reviews and stars from 1 to 5, having a ±1 star prediction is pretty fine. And we can see a more detailed distribution on the right, where we are pretty good at this, knowing that it's absolutely zero shot. But next, what we're going to discuss is actually to review several of the real human reviews, several products, to understand how good our data is and how well our model predicts in comparison to the real values. The first is a movie review. This movie with all of its animals really keeps my grandson occupied when I'm babysitting. He loves watching it over and over again. I can get so much accomplished before he gets bored with it. So it's worth the money. As a matter of fact, I'm buying one for his house, his 3-year-old cousins, and my house. We are saying goodbye to Netflix. Way to go, Amazon. Gaming. Surprisingly, this review is only 3 stars originally, which is odd given the tone of this review. Given how it is written, the model assigned to this review 5 stars, which seems appropriate. The second review, about the tennis racket. The best racket ever made. I have been using this model for around 15 years, and it's still one of the best rackets ever made by Prince. The Prince Graphic Mid Plus is still one of the stiffest rackets you can get, and it also has excellent spades and balance. This racket is more suited to the higher standard players. It provides exceptional control, especially with volleys. I have this racket strung at between 60 to 64 pounds for hard court and grass court play. It will be a sad day when there are no more of these rackets available. And here we also have an example when we have overly excited text and the model assigned to it 5 stars, as I think you would also do. However, for some reason, the review is only 4 stars. There are a lot of such cases. The idea of this analysis was to show you how humans can be inconsistent in such things like giving score, providing a review, and so on, and that actually LLMs can assign score from 1 to 5 much better based on the text description. The next part is metadata extraction. First part was regarding the stars, and the second is regarding all the rest of the metadata. Because here we have not numbers but strings, and actually sometimes lists of strings, we wanted to calculate the consent similarity between them as a pretty standard metric. So what we have done, we have calculated consent similarity metrics between predicted values and labeled values. And after that, calculated precision recall and F1 based on the per row and per column values. And what you can see on the right are not ideal calculations of precision recall and F1, but roughly accurate. And what we can see and understand that actually our model in zero shot predicts all the metadata that we wanted, pretty robust. And again, it's just zero shot without even a single shot. The next one. As a way to improve your custom metadata extraction, there are two ways. Except the basic single shot, few shots, and so on. There are two fine-tuning methods. One is supervised fine-tuning, and the second one is reinforcement fine-tuning. Actually, there are a lot of works that mention that you can benefit with fine-tuning when your task is to basically structure some big unstructured part into the structure for your own model. And we have tested it with supervised fine-tuning, and we're going to use it also in one of our projects using the reinforcement fine-tunings in, we believe, this year. Takeaways. LM performed well in predicting star ratings and extracting key features from the reviews. And the model's prediction of the user feedback rating might hold better justification and lack personal subjectivity. And who knows, maybe soon we will have two product ratings. First one based on the user scores and the second based on the LLM scoring. Or some average value that will be more beneficial to the end consumer. Most of the materials are taken from one of my articles that you can search for. Nowadays we have customers instance, and it's actually a perfect time to be alive. But what's wrong with regular LLMs? One of the issues is level of details. For example, the model knows about BMW, what it does, model names, and some more general information. But the model fails in case you ask about number of sales per year or details of the specific engine part. And the second one is actually specific knowledge. Foundation models are trained at a certain point in time and have some knowledge cutoff date, after which the model doesn't know anything. But mentioning the knowledge cutoff, mentioning the knowledge cutoff, this issue is addressed by Google search tools. Nevertheless, we can completely substitute the knowledge cutoff with the search tool. To understand this, imagine two ML specialists. First, know everything about the current GenAI state, and the second switch from the GenAI to the classic computer vision 6 months ago. If you ask them both the same question about how to use recent GenAI models, it will take significantly different amount of search requests. The first one will know all about this, but maybe will double check some specific comments. And the second will have to read a whole bunch of detailed articles to understand what's going on first, what this model is doing, what is under the hood, and only after that, he will be able to answer. Basically, it's like comparison of the field expert and some general specialist, when one can answer quickly and the second should go Googling because he doesn't know all the details the first does. Main point here is that although Googling provides comparable answer within a significantly longer time frame. For in chat-like applications, user won't wait minutes for the model to Google something. And in addition, not all the information is open and can be Googled. Because we're talking about custom assistants, we surely need a dataset to experiment with. Currently, it's extremely hard to find a dataset that wasn't scrapped and bumped into LLM during pre-training stage, as we can see on the right. That's why we decided to generate a synthetic dataset. We have used the GPT-4o model and 3 simple prompts that you can see on the left, where we asked the model to generate some details about imagined company Ukrainian Boats Incorporated, and want to specify a list of products, prices, and so on. So basically, just like corporate, that looks like corporate documents regarding the company, but imagined for sure. And there are some sequential prompts to proceed with within a single chat. This way we generated the data that looks like the one on the left. When you have company name, we have company overview, we have product lineup with synthetic names, descriptions, prices, and a lot of additional information. And this way you can generate pretty valuable synthetic data set without harm to any private information. And on the right, we have also generated a list of question answers from this corpora, also using the LLMs. We have the data, but now we have to store it somewhere. And for this purpose, we have utilized Neo4j. Neo4j is a pretty convenient graph database that allows you to create not just chunks or nodes, but also create relations, different hierarchies, and has a pretty configurable and convenient UI where you can tweak your data and actually review everything. But actually it can be any database of your own choice that supports vector indices. Evaluation. One of the main aspects of assistance is to know how to relate them. For this purpose, we have utilized the TrueLens framework that has this term called REC triad that consists of three main metrics. First is sound relevance, second is context relevance, and groundedness that measure overall the most important aspects of the system. Basically, how accurately we answer initial questions, how much relevant context do we extract from the database, and how much we ground our answers based on the context we extracted. And those additional information that may be needed. And the result is actually a comparison of GPT assistant and Llama 3.2 assistant. What we can see in this table there are several setups for two different base models, GPT-4 Mini and Llama 3.2, and the difference is suffixes. So we have default retriever that is just basic query tool. We have custom retriever. When we specified custom threshold, we specified custom top K and any additional configurations. Also, we have added tool inputs where we added additional descriptions of tool names and tool parameters and so on, so that because the open source Llama 3.2, very small model, it failed without this additional tool inputs when the GPT-4 Mini was okay with it. And what we can see as a result is that actually the small 3.2 3 billion model answered pretty on the same level, almost on the same level, with also pretty okay context relevance and groundedness, and with almost the same latency, knowing that this was utilized from the API, and this was run on the local 3090 Ti card. And the total cost of the open source model is actually much cheaper. And here it's a total zero because it was a local resource and we didn't rent it somewhere and so on. So takeaways. Synthetic corpus content is pretty interesting and diverse. That's the reason why a lot of models are successfully fine-tuned using the GPT-generated samples right now. And agent call latency of the Llama 3.2 billion and GPT-4 Mini API was pretty much the same, with Llama being much cheaper with roughly same accuracy. And it actually means that for your custom assistant, you don't need to use OpenAI API or any other APIs. You can just use small models. Currently, there are even like mini LLMs from Hugging Face that you can pretty fine use for this test, in case you don't have to reason over big chunks of data. Also, all the details regarding the complete implementation you can find on one of the articles. And yeah, now we have finished with the main part and we can discuss the bonus part. The bonus part actually mentions the situations I have encountered, and that is good to know before you encounter them in the real life. The first one is native language. During the tests of one of our pipelines, we have downloaded a random document from the internet. It happened to be in a newspaper regarding India news. Oh, sorry. Sorry, I want to close. Yeah, yeah, it happened to be an India newspaper. Our task was actually to extract some data into different languages. One was English and the second one was native language. And what do you think was a native language here? And it happened to be that in the English section, the English output from the model, we obtained a correct English data. And in the native field, we most of the time obtain English. Sometimes we obtain Hindi because it's in India's second native language. Sometimes it was something similar to the Chinese that maybe the model itself consider as its native language and so on. And so the main takeaway here is to always specify what is native for you so that the model understands what is native for her. Otherwise, you may finish with one of these situations in your production. Open source models hosting. As a company, we always seek, as a client-oriented company, we always seek ways to reduce the cost for our clients and our services that we provide. And for one of the tests, we have utilized the OpenAI models as a baseline, and after that, thought about cost reduction. One may think that actually the pretty standard way to go is to utilize open source models, and we have a lot of them. On the right, we can see the one of the cheapest pricings for the GPU ranking services. This is a REST AI platform, sorry, that we actually have used on several of our projects. And yeah, you can rent almost anything here at a pretty reasonable price per hour. But after we calculated and tested several instances and thought about how we can scale, how many models we can put in a single graphic card, it happened that this way will be cheaper for us only in case we have almost full load on the system all the time. And it was actually not one of our cases, and I think it's not the case for many customers worldwide. And after that, we have found what is here on the left is the Deep Infra API. What the Deep Infra does? Deep Infra actually hosts the same open source models that we would host here on our own, but it does it via the API. I think nowadays there are much more services that can provide such features, but we have utilized Deep Infra several months ago because it was one of the cheapest and pretty robust provider. And currently, it's actually a big platform with their own even GPU renting services and so on. And actually, the takeaway is that for our use case, it was much cheaper to utilize on-demand same open source models, but not to host them on our own, but to use them as a service. And yeah, in order you're considering some cost reductions and so on, so always consider and benchmark what the actual cost would be, and not think that, oh, of course, renting GPU and hosting a lot of models on one GPU here will be a good way to go. The next is price durability. Actually, we live in the era of production LLMs, agents, and so on, multi-agent systems. And in order to track all of this stuff pretty efficient, we need observability. There are a lot of platforms similar to LangFuse. It's just one of the examples. What actually it provides the pretty convenient log traces, transparency, cost calculations, different prompts, version, and actually a lot of additional features. But the most important is observability. And yeah, actually, it is always good to write logs for some debug and development purposes, but for production systems, you really need a UI where you can trace all of this. Next is cloud pricing. One way thing that actually on the clouds, we should always consider only the compute power and that we pay for, and the rest are just, let's say, 1% of all the costs. But the reality is different. The reality is that sometimes it can be 20, 30, maybe even 50% of the cost when you pay just the cloud provider outside the compute power. On the AWS examples are you store for S3 storage you use, you pay for the requests to the S3, you pay for in each compute resource, for example, Lambda, you pay for the data you transfer outside the Lambda, like requests to the OpenAI, requests to anything else. And of course, the main part is always, let's say, compute power, but the main takeaway is that you always should consider all of them. And otherwise, the real price of your system or of your pipeline won't be expected to one of your clients or to you if you have a product. The next one is color quantization. From the previous slide, you have understood that actually we have to worry about all the different costs. And one of the costs is data transfer out from Amazon, and we pay for each megabyte that we send. And imagine we have any system on the AWS, any pipeline that sends, for example, data to OpenAI to any other provider. And for example, we need to process images or images plus text. And this way we pay for these megabytes that may look not that big, but in case our processing is cheap, then we can send like 20% or 20% of the cost can be just sending the data to OpenAI. That may be not okay for you. And we have also had this issue, and we have researched a lot of opportunities to reduce the cost. And the best we have found was actually to quantize the color space. And we can see that here we can quantize colors from originals to 256 with triple size reduction, but actually pretty same colors. And we can go even further in case it's okay for us, and you can on your own decide how many colors is okay for you, whether it's production, non-production, and so on. But it's actually a pretty good way to reduce costs without losing any accuracy. I think a lot of you know that you can use the OpenAI framework to call OpenAI models, but how many of you know that you can run a whole bunch of providers and models using the same OpenAI framework? There are a lot of companies that support the synchronous integration, where you stop base URL and API key, for example, here to Together AI, and use the same OpenAI framework or the same chat completions, but obtain the results from different models and also pay on the Together AI. That's pretty convenient. It is said that we don't have similar stuff for the asynchronous processing, but maybe in the future, but probably not. And I think one of the last cases is companion documentation. On one of our production projects, we have faced an issue when we had to create the complete documentation for our system, what interfaces we have between different resources, and what data formats we have, and so on. And we have started with the JSON-C files because JSON-C is actually JSON where you can write comments. And it was pretty natural way for humans to read the documentation, but it was pretty hard to maintain. In case we had like 30 files, and after some interface updates, it was really horrible to make all the documentation consistent and relevant. And at some point in time, we have decided to move to the pedantic models for each of the internal data model. So inputs, outputs, and so on. And after that, we have created a custom compiling script that actually compiled pedantic models to this similar looking JSON-C files. So we wrote down all the logic, how to render lists, dict, other models, and so on. And actually, currently we have we can compile hundreds of documents, hundreds of documentation files in like 1 second. And it's pretty robust, and actually it also verifies that you always have same models in the documentation and in the real pipeline. And the last but not the least, actually note that LLMs have their own biases, and sometimes they may play a crucial role in the model prediction. So always keep that in mind when working with LLMs, and don't take all the outputs for granted. Thanks for your attention, and now I can answer any questions if there are.